Hey everybody, so on to our next unit. So until now, we've talked about what the primitives are and how to work with them, what their properties are. And to get them into the frame buffer or on the screen, we've relied on OpenGL to do that for us. So now we're going to learn about how that works. How do we do the math? How do we do the pixels? How do we draw these primitives ourselves? Actually, I want to rename this to manually drawing primitives. Okay. So first, let's talk about the point. Now, luckily, we've actually already covered this back in the data section of the raster when we learned about the raster data. So basically, we just set bits in the frame buffer. No big deal. And the bit order, we talked about that already. However, often you don't get direct access to this, okay? Often it's not directly accessible. Either a library or some hardware might be covering that, and you have to work through an API. And again, just see raster data section. Okay, so points are easy. We just set some bits based on the color that we want at the location. And I won't talk about, maybe I will, you know, this wasn't in my notes, so maybe I'll talk about how the standard ordering, if I have a raster like this, the standard way they're packed into memory is the first line first, like that, and this is byte 0. And then if my width is 100 pixels, let's say it's W, then this last location, last pixel, is W minus 1, zero-based counting. And then the next row just goes in like that. So it's, of course, memory is in linear fashion. You have a big block of memory, and then to access any given pixel, it's typically X plus Y times width. Okay? So if you're in the top row, Y is 0, it's just X. As you move down to the next row, you add the width in. You can think that through. It's not hard. It's not a big deal. You don't really find yourself doing that all that often, but if you do need to index a pixel inside of a piece of memory, this is the location. Now, of course, depending on your byte size, if you're working in bytes, you need to make sure you're aware of the pixel bit depth, right? If it's 32 bits, and that kind of thing. So I'm just glossing over it because it's worth mentioning. And it wasn't even in my notes. I didn't even mean to mention it, but you know, it's good to think about. A raster's in 2D, my memory's in 1D, and there's just a standard way to pack that where you put one row at a time. Basically, our scan lines again. All right. So let's go on to more interesting things. How on earth do we draw lines? Lines are really cool because they're so simple, but it turns out there's a lot of different ways to do it. Now, if I just start from the top, we've said we can put points in a frame buffer by just setting the memory, right? So if I only have points to work with, I now need to draw lines using points. So let's see how this might work. Let's do attempt number 1. Attempt number 1. You can just use your line formula. Y equals mx plus b. This works, right? You can increment x, maybe put it in a for loop through x1. Oops, that should be a 1, not an I. Sorry. Go through x1 to x2, right? You go all through your x's, and for each x, you calculate y I equals m times xi plus b. You can calculate that, and then now you have x, you have y. You can draw at x, I, y, I. Okay, no big deal. So you can do this. You can step through every range of x and then draw a y for it. But there are some problems here. One is, how do we choose the X increment? Right? So I just said we're going from X from 0 to 1. What's our increment? Well, if we're working in pixels, then maybe we could do that. We could choose 1 pixel as we go. But we're not always working in pixels, so we might be, might be in a range of 0 to 1. how close do I sample that function? If I go too big, if my x jumps by too much, I get holes in my line. Okay? Whereas I'm going to draw a line here. I want a line like this. But if I increase my x by too much, you're going to get like a stippled line by accident. You'll get holes, okay? But if it's too small, if I increase my x too small, then I waste work because you end up drawing one pixel more than once. So I draw this a couple times, I draw this a couple times, and you'll get a solid line at the end, but you're drawing pixels too many times. So you can start to think, okay, what's the most optimum? You can calculate how big a pixel is based on your transformation, based on your coordinate space, and you can start figuring that out. But to make things worse, this also depends on the slope of the line. Okay, so let me explain how that works. So in this one here, if I go a line like this, great. If I go x of 1, x2, x3, I step along. Let's say I finally solve it. I use the same algorithm to draw this line. Now x of 0, x of 1, x of 2, you see I can actually skip y. So even though my line might work this way quite well, as I rotate up, I'm going to have more than one y coordinate per x, and that will give me problems. More than one y point per x, right? So if I get more than one y point per x pixel, then suddenly making sure I sample x at each pixel doesn't work anymore. I need to go less than 1 pixel. And so it gets really complicated. So the long story short is complicated. And you end up doing a lot of like how long is the line, which requires a square root. It's not trivial to solve. So it's a good idea, but it's fraught with peril. And actually, I should have a slide on this. Let's see if I can get that going. All right. Here we go. So here's just, y equals mx plus b. But you see, as I go over x, if I'm not careful, I hope it comes through in the video, it's a little stippled. If I take the same sampling that you did for x and y and I rotate the line this way, they get further apart because even though the x sampling is the same, now I need more for my y. And now it gets really complicated. What about vertical lines? Yeah, when x1 equals x2, we have special cases. So you could probably figure it out. I'm not going to say it's not possible, of course, but it's a mess, it's complicated, and there are better ways. So let's look at attempt number 2 that people often think up with. Attempt number 2. Let's make a line. Let's do a second attempt. All right. So now let's use the parametric form. The nice thing about the parametric form is we're not thinking of how many x's and how many y's anymore. We're thinking how far along the line. So remember from your math section, the parametric form of a line is kind of like this, and the beginning of the line is when t is 0, the end of the line is when t is 1, and of course t of 0.5 is in the middle, and the line of course goes beyond that because lines are infinite. We're just dealing with a line segment. So that's nice. So now we can just step along the line. We don't have to think x's and y's. We can actually just think in terms of the line. Oh yeah, I should probably remind you the formula. The line at point t, this is a vector, so x comma y, is 1 minus t times v1, vertex 1 and vertex 2. Vertex 1 plus t times vertex 2. So this is x's and y's. Go back to the parametric equation notes if that still confuses you. So we have this formula, but now the next problem, same with the x. How do we choose the x increment? Now we have to ask ourselves how to choose the t increment. How do we choose the t increment? We have the same problems with the stippled lines. If we're not careful, we get spaces and we get holes. One way to do it is to use the length, GTH, of the line. Let's fix that. So you can use the length of the line which requires a square root, and a square root is very expensive, and lots of multiplications and square roots. By expensive, I mean slow. Okay, it's slow. You also still get rounding errors, so you can still get holes if you're not careful in your lines. So rounding errors, which can lead to holes, which leads you to shrink your t increment. And if I make my t increment smaller, then I get extra work. So it's not trivial, okay? You're stepping along t. You're using ratios and using floating points. You can get rounding errors, so you be conservative. You don't want holes in your lines, so you shrink it. You put extra work. This solution is better than the y equals mx plus b because you get to go along the line in any direction and not worry about x's versus y's, and it's more universal. But it's not a slam dunk. It's not a home run. What other sport? Touchdown? You know, hat trick. What other sports metaphors can I use? So it's not perfect, and it has these problems. So I'm actually going to stop the video there because the next one's a bit long, and we'll learn a new algorithm that you haven't seen before to solve this problem in a much more effective way.